Hello everyone. I'm going to go ahead and start talking about impactors. And the reason I'm thinking about talking about impactors is because of the recent impact, well, it wasn't an impactor, but the recent NEO, near-Earth object, that just passed by this last month. Brings me to think that I might need to jump onto that and spend a little more time describing the impactors, because after all, that is exactly what I'm going for. I wanted to express my theories on tectonic tectonic plates versus vortical tectonics. And everywhere I look on the planet, I just confirm my theories more and more toward vortical tectonics. I'm not the only one that has looked at the Earth and thought about vortical tectonics, but I might be a useful theorist in bringing up some ideas that might not have been seen before or considered. And it was only by mishap that I even thought that there was a possibility that there might be 4 vortices around the planet that are like primary. So this is what I'm going to do, and the first start is going to be on impactors. And of course I want to start with the largest impactor that I believe ever struck the Earth. I could be wrong. The North Pacific Oceanic Impactor may have been larger than this South China Sea Impactor, which I believe is responsible for what we generally see in a circular formation around Indonesia. So it was actually a struggle between calling it Indonesian Impactor and South China Sea Impactor. I was going with Indonesia because of the area, the region, but then when I finally got around to plotting the POP, the POP, which is the point of penetration, I noticed it was right on the Spratly Islands, right there in Indonesia, South China Sea. So that's what I want to go with. I'm going to go with the South China Sea for a name. Now, I can say this, that after further consideration and evaluation of it, I was thinking earlier on that the South China Sea Impactor was older than the North Pacific Oceanic Impactor. However, now I no longer believe that, because I believe that the South China Sea Impactor was in fact the one that was responsible for the North Pole slip, not the North Pole, not the North Pacific Oceanic Impactor. And the reason I say that is because as large as the North Pacific Oceanic Impactor was, I can hardly find any blast rings. Either one, the blast rings were so massive that they go well beyond the 60-degree threshold of being able to view a blast ring on a globe, or they were erased. And if they were erased, it's quite possible, because if the South China Sea Impactor was actually responsible for the North Pole slip, that North Pole slip activity most definitely would have erased much of what you might have seen as blast rings with regard to the North Pacific Oceanic Impactor. And as far as I can tell, there have only been 3, possibly 4 major impactors that had the magnitude to shake the planet into a state of worldwide liquefaction. And so, I mean, good news is, if the planet's really been around for 4.4 billion years, from the point that it had been completely solidified on its shell, then that's only one horrible impactor once every billion years, so 1.1 billion years, I guess, right? So that's not so bad. I mean, we probably have a little, if we could figure out when it happened. But anyhow, I'm going to drink some of my coffee here. Before I go on, I know you guys don't want to sit here and look at me all day. I'm really gorgeous, but I'll have to make you look at my show stuff. So I'm going to go over here to I'm going to hit my PowerPoint. Death by PowerPoint. I know I'm not a very exciting person to listen to, but it's not excitement that I'm after, folks. It's sharing the suggestions I have for evidence of what I see on this planet. And if we start to look at the way all of this activity takes place, tectonic activity, then we could better predict earthquakes and understand what is really going on with our planet. And it's not in the form of plates. I just don't see the plates. I see the vortices, and I see the Earth moving in conjunction with these vortical rotations and the directions of those vortical rotations. So in my first screen here, if you follow my cursor, it might be really difficult to see. I don't know if I ever got a drink of my coffee. Good stuff is cuckoo for cocoa coffee. That's what that is. Just hot chocolate coffee stuff. All right. So right here we're looking at Indonesia in my screen, and you'll see over here from Google Earth I went ahead and captured a screenshot of the coordinate to that distant point that I determined could very well be the pop for this particular event. And you see the red ring following around. That's the red ring that I used. It's a circular tool in Google Earth that you can use to measure circumference. However, I give it another practice. I use it to identify circular formations. Circular formations do not only resemble volcanoes. Not all volcanoes have a circular blast. Some of them are kind of funny looking. Let's take, I know I'm veering off, but I'm giving you an example. Yosemite National Park is actually a twin caldera. This is my theoretical viewpoint, but it has a caldera to the east of it, and people live in it. Yeah, would you want to live there? No, I wouldn't want to. I ain't living in a caldera, thank you very much. But anyway, it's in the, if you look at it from a greater distance, it's in the shape of an oval. So not all volcanoes come to us in the shapes of circles. In fact, not all, well, blast rings for the most part generally wind up being a circle. Blast or pops sometimes will give you the shape of an oval depending on the trajectory of the impactor when it struck the Earth. We almost kind of see that sort of thing happening right here, only that isn't exactly what took place at this particular point. So I'm looking at this slide down here first, and if you'll notice, as we go inside this first area that I refer to as a blast ring, this is the first blast ring. This is the second blast ring. And if I'll remind you that blast rings are kind of like, in a lot of instances, when you see blast rings on the surface of the planet, they're actually more likely from vitrified matter as it reached its fullest extent of blast. So when you have the center of the blast where my fist is and it blows out, all that energy and all that junk is going out to this distance. And then the heaviest material reaches the maximum of its extent of travel and it stops before it gets sucked back in. The thing is, it doesn't get sucked back in because it's too heavy for the residual blast atmosphere to suck it back in, so it gets dropped. It gets dropped in the shape of a ring, and that ring vitrifies or burns the Earth, and it scores a circle in the Earth. You get these in series of like sometimes 3. So you go bam, 1, then it drops mass matter. Bam, 2, you get more mass matter. And then 3, you're like, that's a pretty big burn right there, going all the way around in a circle. Now with Indonesia, as we can see right here, we're not exactly seeing a blast ring in terms of vitrified material coming back down to the Earth. What we're seeing here is far more devastating. And my point of far more devastating is this bugger is huge. So this rock, when it hit the Earth, right, I believe I calculated the size of this bugger. And I believe I published it in my other video where I'm specifically speaking about the South China Sea Impactor. Only I'm referring to it as the Indonesian Impactor because, I mean, if you look at it, it's kind of around Indonesia. But if you think about it, it's pinpointed right into the South China Sea. So which is it? What do we want to go with? I decided to go with the South China Sea. So here's what happens, right? When you drop a huge rock, because I know lots of boys probably do this. You're standing near, even if you're standing near a mud puddle, you're standing near a pond. You take this big old rock. You're like the biggest rock you can pick up because you're like, whoa, check these muscles out. I'm going to drop this rock right here in the water. So you go and you drop this rock right in the water, and then poosh, as that rock goes right through the surface of that water gets displaced. It creates, well, if you had slow motion cameras, and your eyeballs can't really do this, a little beknownst to that boy, such as myself as all was, then you see this great big depression right where that rock fell, where it displaced that water and pushed it out and away. Out, away, and up. It created a crater. So when this rock created this crater in the pond, it splashes up and it comes back down. What you don't see, and what may not necessarily take place with the pond rock, is the pond rock probably doesn't create a vortex. In this instance, the vortex was not necessarily created from the end or by the impactor. The vortex was already there. So if you look just south of that, down here into the North Banda Basin, yeah, it must be a little bit further south in this picture. So we're going to get to that. Well, North Banda Basin is what I consider to be the center of the one of the equatorial vortices that are always there, just like the Great Red Spot on Jupiter is always there. It's always there. It's always going to be there. Whether or not it's really in the same place, who knows, right? You just see that it's going around the planet in circles. Well, we have the same thing in our equatorial vortices on this planet. Only our equatorial vortices have actually 45-degree radii, whereas Jupiter's are condensed. Their radii are much smaller, and they do not have quite the well, they do. I mean, if you were to compare the Great Red Spot to Earth, I mean, scientists have already said that you can get a whole ton of planet Earth into the Great Red Spot, right? So, in essence, it's way huger than Earth's vortical activity around the equator. So, just south of the South China Sea, you have the North Banda Basin equatorial vortex, which is one of the primary 6 vortices on our planet. Yes, the sun has these same vortices. In fact, the sun's vortices are also 45 degree. The gas giant is different. My interpretation of why the gas giant is slightly different is because the core of it is so dense that the vortices are not capable. And when I say dense, I mean more dense than the core of the Earth, because the vortices on Earth travel through the core. They go around it. They just, the core is just like this little nut in the middle, while these vortices pretty much do all their business right around that core. On Jupiter, it's a different story. The core is so dense that the core actually forces these vertical rods around the equator to separate, one to the north, one to the south. The Great Red Spot is one vortex of a 2-vortex vertical rod that exists in the southern hemisphere of Jupiter. So what it boils down to is the similarity is that all differential rotating celestial bodies, as I refer to them, DRCBs, have this same gyroscopic property. Or, I don't know, is gyroscopy a word? If you go to the hospital, it might be. I've got a gyroscopy in my grunts. I need somebody to look at it for me. Well, anyway, going back to the Earth. So here we go. There it is. Follow my mouse. And look at my mouse while I'm drinking my coffee. Okay, here it goes. I don't know, there's my mouth. Oh, hey, you know what? It's going in circles. Woo, hey, in fact, it's going in the same circles that the vortex is going, right? I'm going to show you later. Now, as our vortex in this instance here is going counterclockwise, it is, in fact, rotating counterclockwise. The reason it's rotating counterclockwise is because the North Panda Basin primary vortex is rotating clockwise. The North Panda Basin primary vortex is also the one responsible for the earthquake up in northern Japan here not too long ago, where they were trying to understand why a lot of the land mass up in that region slipped into the Pacific Ocean. That's because it just happens to lie on that vertical tangent, did I say vertical? I meant vertical. That vertical radius of 45 degrees, right on the border of it. And that's where you're going to see the majority of your activity in terms of the Earth having weird things going on, because you have a lot more conflict in those zones. You have less conflict in the center down here and at the core, where everybody wants to rotate the same direction. You have more conflict on the 45 degree perimeters, where everybody doesn't necessarily agree, and they're like, no, I want to rotate this way, and all this other stuff, right? So basically you have a binary vertical relationship between the South China Sea Impactor crater and the North Panda Basin primary vortex. So how do we get that? How do we end up with a binary vertical thing? Well, you see, some wounds never heal, and the planet Earth is still healing, or still trying to heal from this impactor that occurred so long ago. So it's doing this circular wiggity-digit. And when it's going in its vertical direction is being driven by the North Panda Basin vortex. And it began that way because as the material displaced in the shape of a cone, if you might want to call it that, right? It's displaced as a cone, and then as it began to fill back in, already the vortex down here going clockwise, I should say, made this one start rotating counterclockwise. I gotta get my hands right. So as it filled back into this void, it began to go counterclockwise, and this counterclockwise formation and structure is basically what gives us all these mountain ridges that we see in this stuff here. Now, if I go to the next screen up, we're really not looking at much, but you can see that the first blast ring has a radius of 207,733.91 kilometers. But when I start looking at the blast rings of quite a few of these impact sites that I identify, there are some that have a radius of 2.1 million meters to their furthest blast ring. I'm not just making these things up. I'm tracking it. And they're well under, believe it or not, as large as it is, they are well under the 60-degree threshold. So basically, when you're looking at our planet, any point where you look at, that is your point of sight, or your line of sight. And my line of sight in this particular screen, I'm looking at that little line going to that little point right there in the Spratly Islands. And as I look beyond that in terms of radii, and I come out, I can only go out to a maximum of 60 degrees before everything on our planet begins to look like a circle. You see what I'm saying? Because our planet is a circle. So as you get closer to the planet's edge, then you have global distortion, and global distortion in terms of our vision begins to tell our mind that everything you see is a blast ring. So you have a limit on the size of blast rings you can identify, and they have to be well under the 60-degree threshold before you start to skew into the planet's shape. Okay. I'm making this study and these videos, not necessarily for myself, but for our scientists. A lot of the scientists don't agree with me. They only believe, the impression I have is that for the most of them, they only believe that impact craters create ridges in circular formations and have central peaks. This is true in some instances, less true on Earth. Still true, but less true. More true on the Moon. Here's why. The Earth has an atmosphere. The Earth's atmosphere, we all know this, every time a rock enters our atmosphere it burns up, right? Well, that isn't the only thing that happens to this rock. A rock comes in at a trajectory. Here's a little test. I mean, it's just a visual test, but it is definitely, it gives a clue. And the visual test is when you take a pencil and you stick it in a body of water. Say, for instance, a bathtub of water. You stick it in there like this, and as you're looking at it, the refraction of the light makes the pencil look like it goes thick, but you know the pencil's straight. But even though it's straight, it looks crooked, right? Well, this really does happen. Impactors hit our atmosphere like the pencil going into the water, but the impactor's no longer straight. The impactor definitely got deflected. This is what we refer to as deflection. So once it comes in at a trajectory of, then it's going to deflect to a trajectory of, and then you've got the impact of whatever happens, right? Just like smaller stones, you throw them into the pond. You throw them into the pond at a given angle, and then sometimes, even though it's a given angle of, it hits that water and goes, skipper, let's skip some rocks across the water, right? That's called deflection, folks. That's deflection. That's what happens to planet Earth. And when planet Earth has deflection, it causes rounds to come, did I say rounds? It causes impactors to come in at a different angle. And then when they come in at a different angle, kind of a funny one, it leaves kind of like this signature behind. And it looks sort of like, no, it doesn't look like a horseshoe. It looks like, have you ever played badminton? It looks like a badminton birdie in most cases. And you have to really look. You have to look for the fat naked lady sitting on a log. And I don't mean that to be offensive. I mean, I really, size doesn't matter. It's just the impression this is what I thought when I was a child, and my mother pointed, or she didn't point it out. I asked her why we kept this ugly painting in our house. It was a really ugly painting. You're like I was like 8 years old. I'm looking at this picture and I'm just like, why? Well, all I see are a bunch of squiggly weird ass lines. What the hell's going on? What kind of a picture is that? And then my mother, it wasn't until my mother says, "Oh, really look at it. Look at it for a while. And when you finish looking at it, tell me what you think." Well, so when I say the terms like that, it's not Mr. Gemmell as an adult. It's Mr. Gemmell when he was a small boy. And that's when you didn't really want to know who the naked person was, because it might have been your grandmother. That's thoughts the little kids don't really generally care to think about, right? And then you don't want to know who painted the painting. All right, so anyway, because, back in Cousin Joe Bob and Wilma, and Cousin Wilma and they all got together, they weren't necessarily fourth cousins either, right? But hey, one looked good and so did the other, and they were like good with that, so never know. And Grandma, you might be the remnants of such a thing. All right, so as we're looking on to this stuff right here, right, I'm going to get a closer view on here, but if from this point of view, you can look at this and you can see that we have like blast ripples. That's what these are. This isn't the only place on our planet that has blast ripples. When you guys start, and when I say you guys, when I say the viewers start to actually watch the material that I'm presenting, you're going to find that a lot of what I'm showing you is repetitive, and it is. So we have to learn to understand how to identify these different features on our planet. And we got blast ripples here. So after that object struck the Earth, I mean, the theory is that it displaced. Well, it had displacement. Now, it might not necessarily have actually vacated this entire amount of mass, but it definitely had an impact on what that mass was doing, right? And it had enough to come back up in ripples. Now, you notice I have a point location over here that's just to the right, and I'm calling that the Indonesian Cyclonic Vortical Center. So here's what happened. The impactor basically struck just to the west of this Indonesian Cyclonic Vortical Center and created this void, and as the void filled back in, then it started swirling around, and as it was swirling around in this counterclockwise manner, right, its center of its vortical center moved, so it didn't exactly stay vertically centered to the pop. It moved eastward, and this is why you get this clump of land right here in the fine shape that it is. This became the center of the blast area, and it was. This is the vortex. This is the center of the blast area. My bad. This is the center of the vortex it created. So you check this out, and you check out the radii of both of these points, you'll see that the radii of, or the radius of this particular pop is one place, and then the radius of the vortical core is also, you can see it in the shape that it is, right? I don't know if I did that in these drawings. I did it back on 6 March. My memory's not so well anymore. So I'm going to go to the next sheet now. We get a much closer look. And you can't really see. I'm not close enough in to actually see the name of this particular rock out there. But as we get closer, you see the rings, right? The blast rings. And these are the blast rings that they're almost shaped in like a bit of a oval right there. And at first that was my thought. I was thinking oval blast rings. So typically ovals don't generally mean that the round impacted the Earth from the end of the oval. In most cases, you're going to find that the round impacted the Earth from the long side of the oval, whatever you would call that, the oblong. So this is kind of what I would have been looking at. However, that doesn't necessarily agree with what I'm going to show you in a few minutes. Now, I said the badminton birdie. So these shapes of badminton birdies that you see around these pops are what I refer to as B2Ws. I say B2 because there's 2 B's and a W. So it's the blast, give me a second here, B2W, the blast bow wave. Now, where did I get that? Well, you see, these B2Ws didn't have names. This type of feature didn't have a name, and doesn't have a name until I gave it one. I had to give it one so I could explain to people what it is I'm speaking about. And from artillery terms, there's no name for this. It's just a furrow. You're like, well, that furrow over there, or that furrow over there, it's just another furrow. Well, we had to kind of find a better way to describe these furrows. So here you have it, right? Now it's going to be a B2W. Where did I get the name from? I got it from the scientists. Go figure. So the scientists are saying that the, Voyagers 1 and 2 went through space and they found a bow wave. So that's what I'm going to call it. I'm going to call it a bow wave, but I'm going to give it one more name, blast bow wave, because that pretty much is what it is. It's a bow wave that occurs after an object, don't get me wrong with this, penetrates the Earth. And my fingers here don't represent what you think. They represent the hole that was created, right? Yeah, but the hole that was created on the surface of the Earth and this is, my finger's it's not a finger, it's a rock. You got to picture it just the tip. And it goes and it makes this hole and then it blasts things out. Okay. Now that we got that clear. All right. So I could show you right here, but actually maybe I should show you right here before I draw a line on it. Now if you can see, you notice that if you go right through here, you've got a line coming right in through here. It goes right up along this blast stream, and then bam, it starts to go out this way. It's a little bit, it's kind of difficult to see. Whoops, didn't mean to do that. It's kind of difficult to see right here, this close in, but it becomes more visible when you get a little bit farther out. All right. Well, there you go. These are my studies, so sometimes they get a little repetitive, but each time that I save the picture, we're looking at something different. So if I go to this one, right here I have my coordinate to that point. Here I'm measuring the radius. So this first blast stream is 182,460.75 kilometers. Wait, did I say kilometers? My bad. It's 182 kilometers. I can't read. All right. So there it is, right? Yeah. I like to measure them in meters. I think you have the option of measuring in kilometers, but I prefer to actually see it right down to the meter. I like things in meters. So that means you got close to the target. If you're a kilometer from the target, you didn't get close. You know what I mean? Alright. Now, keep in mind, as I'm doing all of these screenshots going down here, my little north symbol up in the left or right hand corner is not true to north. So this is not your true to north view. Why isn't it? Well, because sometimes if I always look at the planet true to north, I can't see what I'm looking for. Don't ask me why. Some things you just to be able to see it, you got to move the planet around until the light reflects your brain or something like that. Until your brain has some way to decipher what it's looking at, and then you begin to see the shape. And this isn't always the case. So I'm not that guy that's like, oh, I'm going to find it because I'm looking for it. No, it doesn't work like that. There's quite a lot of times where I'm looking for it and I don't find nothing. Take, for instance, the evidentiary blast that created Umpqua Ridge in Washington, in the state of Washington. That ridge, and for the longest times, every time I go out there on the OP, I'm sitting down there looking at the impact range. And when I'm bored, I'm sitting there looking at Umpqua Ridge, and I'm trying to think to myself, what volcano around here had the magnitude and power to create these ridges? Sure as heck doesn't look like Mount Rainier had the power to create these ridges. Not when you look at the comparison, especially nowadays, with Mount St. Helens and the ridges it created. Nowhere near what these ridges were, or are, right? So it had to be something bigger. I had to find something that would have been the cause, and I'm thinking volcanism. And then finally, I just happened to be messing around with the theory that maybe it wasn't a volcano, maybe it was an impactor. And then I started looking for an impact site, and I think I found one. And it just so happens that it's not as pristine as this particular site here because it's in the middle of a lake. And of course, Google Earth, it can only present the data that it's given from, the Navy and stuff, and nobody really goes around absolutely checking out the topography of lakes. So Goose Lake happens to appear to be the pop for an impactor that actually would have been responsible for basically creating the ridges that we see, the east-west ridges we see in southern Washington. Yeah. All right. Not sure if you really call it southeastern Washington, but it's southern anyway, right? Yeah. Okay. And there we go up there, and there we go right there. Notice it's still north is off, so I can figure out, because basically my my B2W is coming in here like this, and it's easy for me to see it when it's in the shape of a letter. Maybe that's why, because it's in the shape of a letter. If it's in any other direction, then it doesn't appear to be so much something that I can recognize immediately, right? I have to move it around and think about it. All right, now this is where I determined the what the radius was again of the South China Sea Impactor, POI. POI is point of impact. And we're going to go up. I was going to show a lot more material for this particular video, but it's taken me so long just to talk about this, I think maybe I'll let it go. Okay. Now here's what I like about this picture, right? This picture is a little bit further out. You go down here and you get your elevation at 18,473 feet, right? Yeah, okay, yeah. Huh. Something ain't right. Well, anyway. I was just thinking about something. This is 18,473 feet in elevation above the Earth's surface. And this is how small I can see the whole planet. I must have something wrong with somebody's determination of the height of Japan's wave over the Pacific Ocean, because I could swear they said it was 29,500 feet or some crap, and it's like, no way, I got something wrong. I'm gonna have to go back and look at that, because this is 18,473 feet, and I can almost see the entire planet in my picture. So that's got to tell you something ain't quite right with that whole bank thing, right? You know, the ocean isn't as deep as the planet is wide. Of course, this is not, of course, as deep as the planet is wide, but I mean, it could be graphic, you know, too, but still, that's not what the ocean floor looks like. You can't see the whole planet from standing on top of Japan. It disappears just like anything. Alright, so, now, from this point of view, we have our counterclockwise rotation going like this. You see this little wiggity curlicue right down here. That curlicue is curlicuing right down here in a very, very violent location. Now, I'm going to tell you this right here. These waves that come around here like this wave here isn't like the other waves from the north where it moved in from over on the east and flowed down here and made this great big wiggity-digit. No, this is filling... Doodle, I am trying to speak right here, okay? What? That cut her up. Oh. Alright. So anyway, it's going counterclockwise. And it's going in such a very fast, you see all this stuff moving down here, just really liquid-like. It is very liquid-like. In fact, it happens so very quickly that it's a shock as to how we could probably, I'm guesstimating, of course, because I haven't seen one, but I'm guesstimating that it could probably stand there and watch the ground move. That's how fast we're talking about it moving, right? It's semi-molten hot mass coming all the way down here, building up this ridge right here, coming down here, and whoop-de-doo, it goes in this little curlicue right here and goes woo, 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 woo. All right, that's what it does. And right here is North Banda Basin. If you notice, if you look really close to North Banda Basin, it's oddly in the shape of a pentagon. Pentagon is a shape that we see, I'm pretty sure it's the south pole of Jupiter, and then on the north pole of like Neptune or somebody up there, and it's a pentagon. For the longest time, we couldn't understand how on Earth, how in any world, you could get a pentagonal shape so perfect on a round object, and then we figured it out. It's because there were that many vortices or that many hurricanes basically revolving around the primary hurricane of the core. And I can't remember if they're going the same direction. Actually, I believe they are. And the last time I looked at Jupiter's active storms, they were all oddly rotating the exact same direction. They were not rotating like gears. And that's kind of something you get with the atmospheric gas type environments and atmospheres. They don't rotate like gears. Ground, mass, terrestrial stuff rotates like a gear. Gravity makes things rotate like a gear. So when our parent black hole rotates, it rotates our solar system like a gear, because that's what's coming from it. It isn't heat coming from. It isn't necessarily. Well, it's not solar wind pressure coming from our black hole that gives it the power to rotate our solar system. It's the SME buffers and the SME gauze. SME gauze, the SME buffer combined with the gravity waves. So supermassive gravity waves. Anyway, so that's what you're looking at, and that's why you see a relationship between this binary relationship where they're rotating in opposite directions. So then you get the 5 vortices around, and I'm motioning my cursor where these little vortices are. Oh, this whole section of land right here is right on top of one of those vortices, and you can even see how it's a circle. Come on, people, work with me here, right? All you nice scientists, you. Yeah, you got a circle there, and you got a circle there, and a circle there, and a circle there. All right, this isn't for kids, so I'm safe. This shit was violent, folks. It was not something that took billions of years to form. It happened. It was like, bam! We're going to make you swirl. And sure it did. It came down here. It started up here, came down here, went and all those sound effects actually did happen. I wasn't there, but I bet you if I recorded it, they sounded just the same. All right. Yeah. This is what I'm trying to tell folks, okay? This is not the only thing that this particular impactor did. Now, as you notice right here, if you think about it, this looks like the Death Star. Yeah, that's right. I said it. Star Wars, the Death Star. Great big old eyeball on the planet. Biggest frickin' doggone impact crater on the entire planet. And it's so huge, nobody can see it. So when you get this business going on here, and you have your little foamy core at the center here, where it all bubbled together like like marshmallows in the middle of your coffee, and it's coming around, then you start to see the activity of this coming down here, hitting that, this going, and this going, just like that. It's like, whee! All kinds of swirly ghoulies. Ooh, big going down. Things that make go. Oh yeah, you know what else? This is Japan right here. Right here's Japan. I was almost about to say this is Japan. It's like, oops, this is Japan right here. You see that? Now Japan, it just so happens, if I'm not mistaken, it's kind of part of some of that North Pole slip. So you got some North Pole slipping going on over here and down here, and bloop, 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 getting all mixed up with this guy here. And this is, well, by the way, this is Australia down here in the bottom left. Australia is part of Antarctica, always was, but it has moved north and possibly east from Antarctica. And the reason that is because it broke away from Antarctica, just like that iceberg. The largest iceberg in the world is breaking away from Antarctica. And it's moving toward the equator. Why? Because centrifugal force is pushing it. And it's still going westward. Why? Because the coefficient of solar wind pressure drag is dragging it westward. Hello. I'm going to go into that stuff later. I mean, that was the stuff I was going to drag on about before I got to the impactor stuff. But you know what? We could, by the time I get done explaining all this stuff to everybody and how it works, we might be hit by an impactor. And you know what? It'll be too late, because that's going to be the one that's your money buster right there. That impactor, we've been lucky so far. Everything that we've seen, that we've recorded, has been nothing. That's right, nothing. When we get hit by something that's a something, heads are gonna turn. We're gonna be like, oh my gosh, we need to go back and reevaluate the way we've been reading our planet. And the planet's there to tell you a story. It really can. And those, I'm telling you right now, those stories really haven't changed. China did not. Did I say China? India did not get swept up from the equatorial region into the base of the Himalayas, pushing the Himalayas up. Actually, the Himalayas came down to India and got pushed up. And I'm going to show you how that worked out a little bit later. I already talked about it in my other videos. But we'll talk about that probably in a subsequent video, because this one's taking me so long to go over. I'm just trying to show you guys. It's like, oh, check out all these little whirligigs. Woo! Woo! Whoa! All kinds of whirly-goo-gaglet stuff going on down here, and nobody sees it. Oh, by the way, and everybody's like, why are there so many earthquakes going on around here, around the edge of Indonesia? I don't know. It's really puzzling. Every time I turn around, it's like earthquake activity all going on. I can't figure it out to save my life. Good thing it's not a clock, because they can't find the hand. Oh, that's right. Nobody uses clocks with hands anymore. That's why. Everything's digital. They don't have a digital thingy to tell them it's going around in circles, because the circle itself doesn't really tell anybody anything, right? Oh, it's a plate. Yeah, well, a lot of dinner plates are shaped like circles. That's true. Yeah, but not always. Sometimes you get a square plate. All right, going up. Here's where I'm starting to talk about my B2W. And as you see right here, this white line indicates where, just like I was showing you guys, is my B2W, blast bow wave. And from the center of our blast bow wave, whenever we have something that is a high-angle impactor, such as a high-angle munition, such as mortar round, or is one example of a high-angle munition. In most cases, it's always going to be high-angle, unless somebody hip shoots it, and ain't nobody hip shooting a 120. If you're going to hip shoot, it's going to be a 60, and that's it, yo. So, now, artillery, they can go high angle and low angle. And as far as I can tell, there's only been like one low angle impactor in Australia. That's Little Tully Woolly. And yeah, no, the scientists, at least the one I spoke to, didn't want to believe it or something. I don't know. The evidence is just like in your face, but nobody wants to say, hey, this guy might actually have a point right here. Now, what I'm going to tell you guys is, every time I find an impact site, it has the badminton birdie right there. You see that? Now, this one's a fat badminton birdie. Most badminton birdies come in like that. For the real badminton birdies, they aren't quite that spread out, right? Yeah, no, because then you wouldn't really be able to smack them good. So what this is telling us, folks, is the wider the wings are on a blast bow wave, say for instance our wings were out here, very, very obtuse in their angle, the higher the trajectory, the more direct the trajectory, until it reaches a point where if you have a circular blast ring and a central peak, you basically had a bullseye. You had something strike the planet dead on, 90 degree, like so close to 90 degree trajectory that it didn't have anything but a central peak. Now, when you get anything from a lower trajectory that was affected by deflection, you're going to have it come in, and it's going to be like this. And then the closer these wings come together, the lower the trajectory is until your blast bow wave actually flips. And when it flips, what I'm saying, when it flips, okay, you got it telling a different story. So right now, this is a high angle. Now, high angle has a POO, point of origin, azimuth that is a back azimuth as well, and you take it out the center, from the center of the blast bow wave and the center of the two tips of your wings, and you draw a line, and voila, there you go. There's your direction to the origin of your impactor. And so this is good stuff, folks. You should be recording this. Now, when the things change and we have this strange business that looks more like a bat symbol, where you got the same sort of similar kind of blast bow wave, but in the middle, instead of it just being two wings, you have this kind of like whoop, woo going on there. Whoop, woo. That means your impactor came from another direction. So this impactor came from the direction that you see here, like an arrow. Boop, boop, boop. But when you have a low angle impactor, let's say for instance, hypothetically, if this was a low angle impactor, I'm not saying it is, folks. Listen to me, please. I'm using this as an example for training purposes only. And training purposes only, okay? So we've got this bat wing, we assume, right here. Yeah, you'll see the shape of your bat wing, especially if you look at Little Tully Woolly. Then the center of your blast is going, or the POO for your object is going to be from a different direction. See? So basically, you get a high angle, comes in like this, hits the ground, goes bam, blows back. High angle, bam, blows back. Low angle, bam, blows forward. Low angle, bam, blows forward. That's how I figure it out, folks. It's all based on deflection and schnizzles like that. We'll have the last one go over it. Did you just bark at me? Well, if you'd excuse me, I'm still recording, Booms. People don't make noises when I record, or anybody records. Everybody's supposed to be quiet. Don't sneeze, you'll get doodles started. I don't know. It's funny that she doesn't say at you every time you sneeze. All right, now going back over to here. Now, this is just showing my shape. And we're going to go back up. All right, next one. Here's your eyeball. There's your Death Star. Here, all these other yellow circles are the vortices. So up here you have the Arctic vortex. You have the Antarctic vortex. You have the Lake Victoria vortex. You have the North Banda Basin vortex. And then you have the Pacific Oceanic vortex. All right, so the North Banda Basin vortex is rotating clockwise. Right up here is where that earthquake took place in Japan here not too long ago, where they're trying to figure out why the material is moving into and over into the Pacific Ocean. Well, this is why, because the vortex underneath of our crust is traveling that way. It's in the asthenosphere where it's most active. And so as far as the theories that I have, our asthenosphere is actually the most viscous material that we have, that's like magma, right? And it gets a little bit thicker and weirder when you get to the other sphere. So we got the asthenosphere, and why am I pulling a brain fart? It's not the troposphere, no. Okay, I'll get back to that later. For some reason, I can't think of the other one. Yeah, I don't know why. So now you got so you have this clockwise rotation here, and then the blast here after the material filled back in, it started rotating, going in the opposite direction, and getting chewed up down into here. Now, just because the North Band of Basin appears to not be center of this 45-degree angle does not mean that it is not the vortical core. Its effects, based on its neighbors, determine where its vortical perimeter lies. And the most logical vortical perimeter is in this vicinity here. So, just like, you see the pop is this little yellow dot right here that my cursor is pointing at, and you have a circle right here it's in the center of, but then the center of the vortex is off to the east of that after it began to flow around in Wiggity-Diggits. So now you go over here to the Lake Victoria vortex, and Lake Victoria is going in a counterclockwise direction. So it's basically rotating up. And you notice, oddly, that India is getting chewed up in this blender. Now, when you have these two tangents meet right here, you have what I refer to as a turbulent tangent. On the other side, the east side of the North Band of Basin vortex, where it meets the tangent of the Pacific Oceanic vortex, you have a flowing tangent. When it's flowing, it's because they're both going in like this, kind of like you get in the blender. And then over here, it's turbulent, so you got mass being shoved up toward the north in the area described here as the Lake Victoria vortex, and then you have material being brought down here. Now you'll notice, look at something here. Now, I was telling folks about the Siberian asthenospheric tsunami. So the Siberian asthenospheric tsunami came from the north up here, flowed south, and then was forced toward the west. Well, you can see right here, it was forced toward the west primarily because of the rotation of the North Band of Basin vortex rotating in this direction. It was forced around the perimeter of that vortex to the best it could be, because obviously the force, its own force, was too great for the North Band of Basin perimeter to keep the Himalayas to the west of the perimeter. So it ended up coming down here and flowing out here. Not only did it go here for that particular reason, but also because this vortex is flowing in this direction. So you have arguing flow going on right here. And this vortex, this basically probably came down, and because the North Band of Basin vortex was not as violent and is not as violent as the South China Sea vortex, it did not have quite the influence on the Siberian asthenospheric tsunami coming down here as did the South China Sea Impactors vortical rotation, right? So the mass from the Atlapac fracture, and it's Atlapac because it's Atlantic Pacific fracture, basically encompasses all of the Americas. And so it doesn't split the planet in half, it just at all. So it comes down from the north and it gets forced toward the south and the west. Going south because centrifugal force is tugging it down toward the equator, and going west because it hits and is redirected by the force that is being held right here in the perimeter of am I going the wrong way? I am. In the perimeter of the South China Sea vortex, right? And caught right in the middle of all this craziness is India. India has always been there. It's just getting chewed up, and eventually, it's one side's going this way, so this side of India may escape damage. This side of India is probably going to get chewed up and pulled down here and thrown right into Australia someday. Who knows? But right in here is probably one of the safest places to be on the planet. Actually, when you look at that, well, if you don't think about the Taklamakan Desert right here being a volcanic caldera. Yeah, that's right, folks. When you had this great big mass of of asthenospheric tsunami flowing south and west. It flowed underneath of I can't for the life of me. I'm pulling a brain fart on the other sphere. Okay, so the lithosphere. Okay, so it traveled through the asthenosphere under the lithosphere until it found a weak spot before emerging. Well, it didn't exactly emerge, not like you see Japan emerging over here. It did not emerge. It didn't have. There was too much continental mass right here for it to emerge. So it came up and it lifted the Himalayas up, and they started to flow down over the top of India and stopped where they are today and resting. But at the point that when they stopped right here, that's when the Taklamakan supermassive volcano, because if you take Yellowstone National Park and stick it in there, it's going to look really small. Okay, and this is planet Earth's very own Olympus Mons, right here on the planet, and nobody seems to realize this. And so the lava that flowed out of here went up north and flowed south and west across here, and basically separated the Caspian Sea from the Arabian Sea, and so on and so forth, right? And the Persian Gulf. All of that was connected down here. And it created a land bridge that went across there, which is now Iran, for a lot of it, right? So the other side went flowing here. That's why you see all this funny looking weird melty stuff. It went over here, came down through here. The Himalayas were like, nah, you ain't going this way, bruh. So they had to go like this, and they went back up north and then east and then went down here. Now, because of the coefficient of solar wind pressure drag, the lava is forced south. Well, centrifugal force is what forces it south toward the equator, and the coefficient of solar wind pressure drag is what's forcing it westward. So it's coming down and it's flowing down in here, feeding into this already very volatile region of vortex from that impactor. Woohoo! This stuff happened really fast. So when you think about it, it all happened like ooly gooly goo, going around like, Play-Doh and stuff. That's the story you got there, folks. And that's only the Siberian AT, or the Siberian asthenospheric tsunami, right? So they don't always stay in the asthenosphere. They pop up. They pop up and they start to come out onto the Earth's surface, right where you can see a whole bunch, just like what we see in Hawaii when, I think it's Kilauea starts to burp. And burps up a bunch of red vomit, and it just kind of like, rolls. But this stuff here, the only way you're going to get a wave action like this is if it's highly viscous. This is highly viscous activity with smaller vortices here. Turbulence like you wouldn't believe. Turbulence like you see in the rapids going down a river. This is the kind of stuff, that's how fast I'm talking about. We're talking about rapids of the Earth's surface. This is the scary stuff you don't want to be standing on when it's happening. Okay, and this is the kind of stuff, not only would this impactor have created, or basically shielded the Earth from the sun in this humongous, horrible cloud of, but all of that material blown into the atmosphere from Taklamakan would also have filled the atmosphere, very likely throwing our planet into a global ice age. Well, that sounds kind of familiar. All right, so yeah, we're going on to the next one here. And, well, so this is just another picture of all the other stuff. And then you see my blast bow wave here as I'm perfecting my picture, as I'm going to display it. And we're going up here. Sometimes I change things depending on further analysis. And I come up here till I get to right here. Now you notice it looks like I pretty much centered north to where it should be oriented. And now you see the actual direction as it would have appeared in relation to how we normally look at our planet, with the North Pole where it is. Then we go up here to my graphics. Now this is the thumbnail graphics that I presented for, and I'll go to this screen because this is the one I saved before I made it a picture, that I made for the other video. And so we see the directions. We see the Lake Victoria vortex direction of rotation going clockwise. The Arctic vortex is going basically clockwise, and which means that because these two, the Arctic and the African vortices, are going clockwise, the tangent you would have at their contact points over here would be turbulent, a turbulent tangent. And then over here you have the Pacific Oceanic vortex going counterclockwise, and the did I say a direction wrong? I might have said a direction wrong. So this one's going clockwise. This one's going clockwise. So you have clockwise and clockwise, turbulent tangent, clockwise, clockwise, turbulent tangent, clockwise, counterclockwise, flowing tangent, clockwise, counterclockwise, flowing tangent. Turbulent, turbulent, turbulent. So you have three turbulent tangents. No, these are this one. This is so confusing. So I have turbulent here, where the arrows are going in opposite directions. Turbulent here, where the arrows are going in opposite directions. Then I have flowing tangents, where the arrows are going in the same direction. Flowing. So you have flowing, flowing, turbulent, turbulent. So yeah, I don't know why I started thinking about the other stuff. I was like, wait a minute, I'm getting myself confused. All right, so the white gizzity goo is my South China Sea B2W. That is your signature indicator of an impact site. And then, of course, I give you the perfect pentagonal shape that I pulled off of up here. You get all these little wiggity-doo shapes, and yeah, it came right off of up there. Notice how well it seems to fit right there. Isn't that great? That's so crazy. And notice that my little directional rotation thing right here is describing how this the center of this vortex is. Now, it could just be, ladies and gentlemen, that the North Banda Basin, true to be the center of the equatorial vortex in this region, is off from where you would expect it to be. It could just be that the impactor pushed it before the ground solidified a little bit better. You know what I'm saying? So this is what you see now is the frozen ground as it solidified once again, as it was pushed away from the impact site. And it could just be that is no longer the center of our vortex. Our vortex core might be more like where you would expect it to be, right around in here someplace. And I'm going to tell you this right now, these on Earth, these vortical cores migrate. And how do I figure that one out? Well, oddly, in the Pacific Ocean, I was able to vaguely, or I don't know how to say it. Excuse my nose. Basically, there's like a helical. So the helical starts up in like the northeastern region of the Pacific Ocean. Oh, in the northeastern region of the Pacific Ocean, and it just goes to where it is now. And so you got this helical a helix going all the way from this point down to where it is now. Ladies and gentlemen, that's telling you something. That's telling you that the Pacific Oceanic vortex has migrated from up here and moved to where it is today. That means that the planet is so dynamic that these vortices, these primary vortices, though their existence is permanent, their positions are not permanent. Does that mean anything? So, what does it mean when the vortices positions, the vertical core's positions are not permanent. What does that tell us? It tells us that the North Pole migrates. And it's not just back in like 1966, the North Pole moved like 3 degrees somewhere. Not sure where, but it did. But I know it. I read it somewhere. Well, duh. Okay. Now my point is, if you take the world and you put it up on this flat piece of paper and you get it all skewed at the north and the south at the poles, where Antarctica looks like this really long, stretched out, horrible thing, and then Greenland looks like some sort of continent that's larger than every continent on the planet. So when you get that there, you try to ignore the skewing of the global distortion that is very evident in these flat maps. Okay, now you take an objective viewpoint and you bring yourself to imagine the center of all of that continental mass as if it was all right back into one clump called Pangaea. All right, now, understand, Earth had 2 continents, Pangaea and Antarctica. Antarctica has always been there. Australia was once part of Antarctica, which means Antarctica has always been there, and at the South Pole. And then you had all the lighter masses, because Antarctica is the hot chocolate and sugar that got dropped to the bottom of the mug because it didn't get stirred in quite right. And then you get all the fluffy foo, marshmallow crap went all the way to the top, and then you have all the in the middle. So when there's happened, Pangaea is on the North Pole. Well, it just so happens that the visual center of our Earth kind of puts you right at the northeastern shoreline somewhere like right on a peninsula, maybe not even in there, maybe it was in the water of the Caspian Sea, which, oh, by the way, if you look at it, it's got a swirl. Swirls mean vortex. Anytime you see a swirl, ladies and gentlemen, there was a vortex there. And when you start to look around up in the Nunavut area, go ahead, do that now. You look it up. Look at the frickin' Nunavut stuff. You will see how turbulent that ground was. There are vertical swirly cues all over the place. You're like, oh my, now volcano do this? No. The Earth has vortices just like Jupiter. You just don't see them as much because they're underneath. When the Earth solidifies, after the planetary sutures came together and said hello. That's right. Earth was a baby once, and its skull had to come together. Just like the baby's skull. Same stuff. Physics repeats itself over and over, and so on and so forth. I pretty much beat this thing to a dead horse. So there's what you got right here. Now this is going to be my Wednesday video, and it's going to be the start of what I'm going to begin describing, and I'm going to go into somewhat greater detail, because at some point I determined, and apparently it wasn't in this particular stuff here that I made a determination what the size of the impactor is. You know what I mean? I'll have to look through my notes. But this impactor was big. It was bigger than a lot of their other impactors. I'm thinking if my memory served me well, it was somewhere around 19.4, either 18.4 or 19.4 kilometers in diameter, if it was even a round ball. We're assuming it's a round ball. And no, I didn't just pull that dimension out of my butt. If we use Meteor Crater and the scientific theory that Meteor Crater's impactor had an approximate diameter of 40 meters, and I say approximate because they said it's anywhere from 30 to 50 meters in diameter. So we'll give it an average, 40 meters in diameter. So a 40 meter in diameter impactor that has the magnitude to put a hole as large as the Meteor Crater in the Earth, then that's basically what you go on, and you consider the perimeter of that hole to be your primary blast radius. After further analysis of Meteor Crater, I can see that there was more than one impactor, and it could just be that the primary impactor broke up into smaller impactors, but there are approximately 4, if not more, smaller blast rings within the bowl of this crater, you see. So we just kind of have to, it pretty much was a bullseye, so you're not likely to get what you would expect to find. And oddly, for it to be considered a crater, I'm not sure that I recall ever seeing a central peak, and I was told that if it doesn't have a central peak, it's not a crater. So, well, if that's the case, then Meteor Crater is not a crater, because I'm pretty sure there's a building there, and there's no central peak poking out of the ground. So anyway, right? That should tell you something. So that's basically what it's based on. So this impactor is pretty large, and I think the one that just passed us last month was like 1 mile, I think they said, 1 mile long. I don't think they gave it a diameter. They just said it was like a mile long. It was like a flying cigar, or a flying Volkswagen. That's what we call rounds that go through space, go through the air, not space, but go through air right over your head. If you hear them go, that was a round that had a wing broken. Yeah, we called them flying Volkswagens because we were in Germany, right? Good thing it didn't land on our heads. I mean, you could hear that thing flying through the sky. It's like, yeah, it's pretty cool stuff, you know. So anyway, there you go. It would have been a flying Volkswagen, which might have been a little bit, might have hit the earth a little bit more strange. It definitely would have broken up. It wouldn't have been able to stay a Volkswagen, I don't think. So that's what you get, right? So yep, you got all these stuff now. Considering the fact that I don't think in terms of miles, I have to Google how many meters are in a mile. Figure that stuff out. Go figure, right? And so just imagine, take your mile, figure out what a mile is in meters, and then compare the length of that particular impactor. Well, it's not an impactor. It hasn't impacted anything yet, so it's just a NEO. So take the length of that NEO and convert it to meters, and compare the meters of that particular NEO to the estimation of the South China Sea Impactor. Size and diameter being somewhere approximately around 19.4 kilometers in diameter. All right, that concludes this video, and this is going to be the first of my series of videos where I'm going to start identifying all of the impact sites that I see and describing why they have so much in common. And oh, by the way, something I didn't mention is the Bermuda Triangle. There might be a reason why there's a lot of magnetic weirdness going around there. And if you think about it, go to Bermuda Rise. Yeah, well, everybody says, well, if a impactor, or if a crater is not a crater unless there's a central peak, well, why is it no one has looked at Bermuda Rise and said that's a central peak? Well, guess what, folks? The Bermuda Rise is a central peak, and it's the pop of an impact site. So if you have a lot of magnetic weirdness going on there, it could just be that the object that struck the Earth at the point of penetration, where Bermuda Rise is sitting right now, might have been ferromagnetic. You know what I mean? And carrying some really good weirdnesses. Maybe that's a good point to start mining some iridium. Well, anyway, here's what you go. This is going to be on my series titled, let me think about it. What am I going to call it? I'm going to call it Gemmell's Meteor Impact Atlas. Yeah, Gemmell's Meteor Impact Atlas. There you go. So be sure to like and subscribe. Okay, that ends my show. I'm going to figure out go down here. I still haven't figured out how to turn this off where people don't have to watch me going to turn it off. Okay, bye.